Welcome, guys. In this video, we are going to study local linear approximation. We will try to approximate our function near vicinity of a point using its tangent line. For instance, let's take a look at the function y is equal to x squared plus 1. If we magnify some portions of a graph large enough, then we can see that function resembles a straight line. Now recalling an equation of a tangent line to a graph at point x0, which is equal to f at x0 plus derivative of function at x0, x minus x0. This is an equation of tangent line to graph of f of x at point x0. Now, if we are in a vicinity of a point x0, in this case x0 is equal to a, then we can approximate values of function f at x using an equation of the tangent line at point x0. In a case when x is close to x0. We can also use the following notation by replacing x minus x0 as delta x. All right, now let's use local linear approximation to solve the following problem. All right, so let's find the local linear approximation of function f of x equal to root of x at point x0 equal to 1. So derivative of function f of x is equal to 1 over 2 root of x. Then we are approximating the values of our function f of x using an equation of a tangent line near point x0. So substituting values of x0 equal to 1, we'll get the following equation. 1 plus 1 over 2 x minus 1. So here is our local linear approximation near point x is equal to 1. Now use local linear approximation to approximate a root of 1.1. So then our value of x is equal to 1.1. We are using tangent line approximation near point x is equal to 1. So substituting 1.1 here, we'll get the following value, 1 plus 0.05. And now let's compare our approximation to the result that is produced by calculator. So root of 1.1 using calculator is approximately equal to 1.048. And we can see that our local linear approximation gives a good approximation to the actual value. Now we are going to study how to present derivatives in a differential form. So up to this point in this course, when we were looking at derivatives, we were using Leibniz notation dy over dx, where dy over dx was treated as a single entity representing derivative of function f of x. Now, we are going to treat dy over dx as an actual ratio by assuming that dx is some variable that can, independent variable that can take on any real value, and then dy is our dependent. dependent variables. So then if we treat this as a ratio, then we can express dy as f prime of x multiplied by dx, which is known as a differential form of derivative of function f. A geometrical meaning is following. So if we look at curve of function f of x, let's take a look at an arbitrary point x. Then the slope of tangent line is presented as f prime of x, and it represents a tangent of the following angle theta of a tangent line. Which is equal to the change in y when we are looking at an equation of a tangent line over the change in dx. And the slope of tangent line at an arbitrary point x is then given as derivative of that function at that point x. So then if we look at dy and dx as separate entities, as separate variables, and we can express dy as f prime at x multiplied by dx, which is known as differential form of a derivative. Now let's use it to solve the following problem. So let's express the derivative with respect to x of y is equal to x squared in differential form. And let's discuss the relationship between dy and dx at point x is equal to 1. So derivative of function f of x in our case is equal to 2x. Then dy is equal to 2x multiplied by dx. All right, so meaning of that is when we are looking at the value x is equal to 1, dy is equal to 2 multiplied by dx, which means that when we travel along x by 1 point, it produces 2-unit increase in values of y. So for instance, if we travel 2 units along our x-axis, then it produces 2 multiplied by 2, 4 units increase in values of dy when we follow tangent line. Now, it is important to make distinction between delta y and dy. Let's take a look at the following graph. Delta y represents a change in y when we travel delta x distance along our curve of f of x. So delta y is a change between the values of y at a point f at x, at an arbitrary point f at x, and at point f at x plus delta x. When dy represents a change in y when we travel distance dx, if we set dx is equal to delta x, when we travel distance dx in y direction along the curve, along the tangent line. So dy is this change in values of y when we travel along tangent line. All right, now let's solve the following problem. Y is equal to root of x. Let's find formulas for delta y and dy. Delta y represents change in y coordinate when we travel along our curve root of x. So this is f at x plus delta x minus f at x. So this is change in y coordinate when we travel from arbitrary point x, distance delta x. And since f of x is equal to root of x, this is root of x plus delta x minus root of x. Now dy represents change in y coordinate when we travel distance dx along tangent line to the graph of our function f of x at arbitrary point x. So this is equal to f prime at arbitrary point x multiplied by dx. Derivative of our function at arbitrary point x is then equal to 1 over 2 root of x multiplied by dx. All right, now let's evaluate values of delta y and dy at point x is equal to 4, and dx is set to be equal to delta x and is equal to 3. So delta y is then equal to root of 4 plus 3 minus root of 4. So this is approximately equal to 0.65. Now dy is equal to 1 over 2 root of 4 multiplied by 2 multiplied by dx is equal to 3. So this is equal to 3 over 4. Now we can see the distinction between dy and dx. So dy here represents change in y coordinate when we travel a long distance of 3, dx is equal to 3, a long tangent line to our graph at point x is equal to 4. And delta y then represents a change in y coordinates when we travel distance delta x along our curve root of x. All right, guys, now this concludes our section on local linear approximation. Thank you for watching.